Okay, I think it's recording.
It, I don't think it is. Is it?
When
Are
you
you good?
signed when you
It
signed
says
in, did it
recording every
make
time.
you the host?
Okay.
Okay,
Yeah,
we're
that looks like
recording.
Are
it
we
is.
good? All right.
We're good.
All right. Welcome to BS&BEER Canada. For those of you who don't know me, my name is Aaron Jones. I am a carpenter and a builder on Grand Manan Island in New Brunswick, Canada. Tonight, though, I am joining you from Massachusetts outside of Tupper Hall at Etobicoke College at the Fine Home Building Summit. I am in an Advantech koozie. I am drinking a Samuel Adams Oktoberfest. I am extremely grateful and excited for our guests this evening. But before we get into that, I am going to hand it over to Lori because I have 15% left on my phone. See everybody later.
Thanks, Aaron. Hi, everybody. I'm Lori Rand. I am joining you from Halifax, which is just over my left shoulder on the far east coast of Canada. Um, I am really excited about this. Anybody who knows me knows that I am a pretty big deep retrofit nerd. And so very keen to hear the details of the project that we're going to talk about tonight. I'm drinking what I believe is like a yellow label store brand fizzy water. I do not have anything alcoholic in the house and I don't need any. I have to confess to you guys, I've been awake since about 4 this morning. And so if by the end of this, there's just a chair here, I do apologize. I actually am really excited about this, but I might fade. I also wanted to say I'm going to be the end of next week. I'm going to Maine. I know we have a few folks tune in here from Maine some nights. I'm going to be in oh my goodness in Freeport because there's a retrofit symposium put on by Pass Maine. So I've been lured across the border. I haven't been since your current president was elected, but yeah, I'm actually getting excited about it once I made the decision to go. So if anybody is in the neighborhood, come say hi to me. And I'm going to pass it over now to Justin.
Hello, everyone. Justin Ott from the Flat Plains of Saskatchewan. We are a custom home and renovation company focused on building science, building envelope first approach. And yeah, really excited to hear about this project. And yeah, over to Jeremiah.
Good evening, everyone, and I'm really excited to be to part of this side of the panel. I really enjoy following these shows and hearing the various guests that have been on, and I'm excited to be on this side for a change. I'm Jeremiah Summer. I'm a builder in Southwest Ontario, and along with my brother, we own and operate residential and some light commercial new home and remodel business, and a lot of our focus is on building enclosures and utilizing building science to help us improve what we do every day. I'm also really excited to hear this presentation, and while we're hearing it, I'll be drinking a Sober Carpenter Irish Red tonight, and I think that's probably good for me, but I'll introduce our guest tonight. Tonight's topic is Deep Energy Retrofit in Net Zero Ready project, and our guest is Jonathan Smegal. Jonathan is a senior building science consultant at RDH, and some of his work includes laboratory research on hydrothermic modeling, field monitoring of wall performance, and forensic analysis of building failures. This particular project is quite interesting. It actually basically follows three townhouse projects that were renovated and upgraded in a deep retrofit sort of manner. And I'm sure Jonathan will have a lot more to say about that. So I'll turn it over to Jonathan. And if you want anything else to add to that, Jonathan, go right ahead. And what are you drinking?
Thanks, Jeremiah, and the rest of the BS&BEER Canada people. As you can, so you can see my, sorry, you can see my presentation, correct? Yeah.
Not yet.
Working?
We see you.
Okay, hang on. I'm gonna reshare it. I thought I shared it.
All good.
Screen two, share. There we go.
There we go.
See it now?
Yeah, got it now.
Perfect. That's why I was having it. Okay, that's why it looked a little different. All right. So thank you, Jeremiah. I am at RDH. I work in the Waterloo, Ontario office at RDH, where I've been there since we joined RDH 10 years ago. And I was even there for the 10 years previous to that in the same place. So I've been doing this for quite a while, kind of an enclosure specialist. Started off doing a lot of lab research and then moved more into the construction field. In honor of the beer and building science, I want to share these two photos. This is where I am right now. I'm at Penn State, and so this is the home of the where the R value was apparently first defined and decided on. And then the beer I'm drinking, I just picked up a few minutes ago on my way to the hotel, and it's that in the bottom corner. It's Leaf Seeker. I just like to go places and pick up a local beer. So it does taste pretty good, I will say. So that's what I'm drinking. Let's see, we got disclaimer, a little bit about the outline. So we're going to talk a little bit about deep energy retrofits in general. Then we're going to get right into the case study and talk about what was done there, how it was done, the different components of it. And then we're going to, after we talk about how it was constructed, we're going to look a little bit of data analysis from the enclosure monitoring system that we installed. In this project, we had a relatively small role. We were hired, RDH was hired to do a design review, to work with the architect, between the architect and all of the building product manufacturers to determine some of the details for those systems, because as we'll talk about, there were different systems and different details. And in addition to that, we were on site a few times reviewing construction informally, but more importantly, we were installing sensors in the wall systems during construction because we had to go a few different times to install those sensors at the right layers so we can measure the performance in terms of the moisture content, the temperature, and the relative humidity. But we'll get into all of that. You can see here just a pie graph showing the number of buildings. This happens to be in the US, and you can see the single family homes is a very large percentage of all of the buildings in the United States as of this 2020 report. What this graph shows is just the annual global CO2 emissions that are based on buildings, building operations, building construction industry, and other construction industries. And so one of the goals of deep energy retrofits is obviously to reduce the CO2 emissions that we emit both locally and in regions and nationally and around the planet. So that's one of the main priorities. There's different reasons to do retrofits, but one of them, and the biggest one coming out these days, is to reduce the greenhouse gas emissions and global CO2. So the first question I like to ask is, what happens if the government mandates retrofits for existing buildings to reduce greenhouse gas emissions or to reduce CO2 emissions? And I'd like to start by just showing this table of things that are currently going on right now in different regions. This is not by all means, this is not all of the actions that are going on in different regions, but this is a few of the ones that I'm most familiar with. And you can see that in Toronto, in all of Canada, in Vancouver, Washington, New York City, Boston, all have these goals that are very specific and have pretty far out deadlines, and they're trying to meet all these greenhouse gas or carbon dioxide emission levels. And in order to do that, we're going to have to make major changes to both new construction and existing buildings. Not so much the new construction; they are way more energy efficient than they used to be. Obviously, when we look at the historic buildings and the uninsulated buildings, but it's going to be a strategy that includes all types of buildings, both new and existing, in order to meet some of these goals and all the other goals that I can't include on this list. So it's not really what happens if the government mandates retrofits. Obviously, it's the only way they're going to meet these goals is by mandating or having programs or rebates or things that include retrofits, because there's no other way to do it. There's so many buildings that exist already that we can't do it just by picking the new construction and even doing great new construction jobs. We have to work on the older existing buildings. And so these are the kind of the types of retrofits that we like to refer to when we're talking about a retrofit project with a client or with someone that's thinking about doing it. Is we have light retrofits. You get a small greenhouse gas reduction. Moderate retrofits, you start to get into more of the gas heating upgrades. Deep retrofits, you're moving in most regions, you're moving to heat pumps, enclosure upgrades. And then there's other things we can add into that, like sizing upgrades, climate adaptation measures. As the temperatures around the world are changing, sometimes we need to change the design of these buildings and future-proof these buildings for some of the things that we expect to happen, as this building exists. Because we don't build buildings for the short term, we try to build buildings for the long term. And so what the building sees in 30 years could be significantly different than what it sees now. So we have to keep that in mind if we're doing a deep energy retrofit as well. And we like to say that every building needs a deep retrofit plan. And so if we're doing a deep retrofit, what are the stages? What are the things we need to think about? And so usually it starts with, we add insulation. We need to make the building more energy efficient. We want to lose less heat or gain less heat, depending on where it is. In Canada, we obviously want to lose less heat for most of the year. We want to improve the windows and we want to improve the air tightness. Air tightness is a big one. We can't, if we add all this insulation to the building, but we still have a very air leaky building, we get all the energy losses anyway. It just bypasses the insulation that we've added. So that would be the first step. Then we talk about energy efficiency measures, lighting, heating, cooling, ventilation, all of the mechanical equipment goes into the energy efficiency measures. Typically in a deep energy retrofit, at least in Ontario and other places, we want to decarbonize gas systems. We want to fuel switch to electricity. We want to use ground source heat pumps or air-to-air heat pumps. On the case study I'm going to talk about, we did 11 townhouse units and 9 of them had the gas meters removed. We did keep gas in a couple of them, partly because in other places in Ontario or in Canada, removing gas completely doesn't make as much sense as it does in some areas. So we wanted to have a couple of those in the project to see how it performed compared to the other ones. We can go net zero or net zero ready, which we did in this project. We don't have to. We could just do the first 3, but we could talk about renewable energies, wind, offsite or onsite PV. And then, from my background, we always want to measure and verify. We want to measure the energy. We want to measure the fuel consumption. We want to measure the performance of the walls if we can. And so we did that in this study. We have lots of loggers and data analysis, and I'm only talking about the enclosure monitoring. There's another team that's looking at the mechanical monitoring and the energy, that side of things. And my understanding is hopefully they're gonna make some presentations, and now that we have 2 years worth of data, and be able to make some comparisons on how that equipment worked. But they haven't yet, so we're waiting for that. So some of the drivers for building owners to undertake a deep energy retrofit, some of these are obvious, some of these are a little less obvious. When things need to be replaced or repaired, sometimes it makes sense to just go a little bit further and do a deep energy retrofit or an upgrade to things. Like if your cladding needs to be repaired, or if your brick is falling off the building because it's a 150-year-old brick and you can cover it up, then you might want to do that, things like that. Regional changes, so reduction in carbon or GHG, like at that table I showed, or increases in carbon taxes, those types of actions by governments and municipalities may drive the necessity to do a deep energy retrofit. Sometimes we are investor driven, so they won't invest in a company or business unless that company or business can show that they're taking steps or have a very low CO2 emissions goal for their company. Leasing requirements, so often it's becoming more and more popular that a company may not lease a building unless it's energy efficient. They want to be part of the solution, less of the problem. So they're only going to lease buildings that are that don't release a lot of CO2 in their operation or in their construction. Obviously, when we do a deep energy retrofit, we should have lower energy costs. We should have increased comfort, which is hard to, you can't put a monetary value on that, so it's harder to explain to people. And some people just do it because it's the right thing to do. And as silly as that sounds, some people that's the reason they do it. All right, so we're going to get into the actual case study and talk about that. The project is in London, Ontario. It involves Fanshawe College. They also have University of Western Ontario in the city. You can see the climate, the heating degree days there, climate zone 5, just kind of on the edge. And so, like I mentioned, the scope of work for RDH was just, we weren't, we didn't do the large enclosure scope on this one. We were design review, reviewing drawings for the architecture firm, talking to the different manufacturers, kind of liaising between those, trying to figure out what details should look like in a lot of cases. And then we did the enclosure monitoring, but we happened to be on site a few times and could provided some input or some insight into some of the details while on site. So the whole project kind of started back a while ago now, actually, because the whole thing took a while to get going. But in 2018, there was a Leap for Renovators Technology Forum in London, Ontario, and it was attended by design professionals, builders, product manufacturers. So basically, it was an opportunity for builders and retrofitters from London, Ontario, to come listen to product manufacturers and building scientists talk about how to do retrofits. So I started with kind of the building science related topics of all retrofits, what we're looking at, adding R value, decreasing air leakage, those types of things when it comes to retrofits. And then a series of manufacturers came up and kind of gave what they thought would be a good option for a retrofit of an existing building from the exterior. And so based on that, Fanshawe College was there. Tom Davis, formerly at Fanshawe College, was a huge driver in this program for Fanshawe College. And so he saw an opportunity to use the information and the solutions that were implemented there to do retrofits on a block of student townhouses on campus. And so there was a secondary workshop just on mechanical systems, not on the enclosure. But it turned out these buildings were in need of upgrades. They were getting quite old. They were looking a little worn. I mean, they're student townhouses, essentially. They were built, I have it somewhere. I don't remember the exact year, but they have 2x4 framing. They have an R12 bat, and they didn't have wood sheathing, which made the whole thing a little difficult in some of the details. But they had R5 XPS insulated sheathing, and they had R12 bat on the interior of the foundation for 2 feet below grade. So that was kind of typical of that time. You can't remember if it was the 70s or 80s, but and so this is how I like to throw this in there, because LEAP is a government organization that does help promote these things. They have a lot of resources on their website. Right now, they're working on a whole series of retrofit papers or documents that are aimed at like homeowners and contractors that are less knowledgeable. Like they kind of try to simplify things and to talk about different areas of the building, different retrofit ideas. They're going to be out shortly. It'll be a good place to go to find information for homeowners. But they provided a bunch of funding for this project. And so the LEAP process is, as I said, there's a builder planning workshop that I was part of, technology forum, and then we're going to field trials, and then they publish the information online so they can share it with everyone. They don't want to just hide the information that they learn and that the lessons learned. They like to share with everyone so that everyone can benefit from this. And so because a lot of people are less familiar and are less comfortable with some of these new technologies or these new materials, and so it helps to get it out there. So the objective of this project in general, the first one, the overarching one, was net zero energy ready certification. They wanted to lower the global warming greenhouse gas emissions from these buildings. They wanted to do technology transfer, construction details, develop a whole lot of construction details that they could share with others if they were successful, especially. They worked with 5 different insulation manufacturers to develop the deep energy retrofit solutions and multiple HVAC manufacturers. We'll talk about that briefly, but like I said, we're not going to get into the weeds on that. They wanted to monitor and report on actual performance, which is always key. We love to hear that. There was a bit of a project debrief, and then, like I said, more dissemination, many options for research papers, presentations, homeowners, professionals. Try to share this as often and as much as we can. The project started with some energy modeling. They wanted to determine how much insulation they needed, what types of systems mechanically they wanted to include. And so that was done with HOT 2000 and a Housing Technology Assessment Platform, or HTAP. And so in case you're unfamiliar with HTAP like I was when I started this project, I gave a little definition here. It brings together building performance simulation software, building stock data, energy conservation measures, rule sets, energy targets, economic. It just basically brings in everything you could possibly put into a model that has to do with the regionality of the location in London, the costs, everything that has to do with that, and then it kicks out a million options or a million different scenarios. And so it was conducted at Building Knowledge Canada in this case. And if you want more information, there's a link there you can get. But this is basically the output. Every one of these dots is a different set of variables. And so you can see at the top, I don't know if you can see at the top or not, but they talk about the blue are all air source heat pumps, the orange are all cold climate air source heat pumps, red are hybrid, and green are no change. But you can see that the total retrofit costs, and of course there were other variables like the amount of installation and R values and wear and those things. And so you can see the total retrofit costs on the y-axis on the left, and then the energy savings on the bottom. So, I mean, generally speaking, the more energy savings you have, the higher it gets. But there's a whole bunch there near the top, or near the right side rather, where you can get a lot of energy savings and your costs haven't gone up substantially. So, an interesting exercise. Like I said, I'm hoping that they can give some results on the energy savings and see how it compared to the actual choices for each unit that were made. Because it's always nice to see that. Historically, models have definitely got a lot better. I know when I started in this industry, they were plus or minus a lot, and now they're plus or minus less. So, but it all depends on the user experience. All right, so the enclosure of these Kessler Court Deep Energy Retrofits. We wanted to increase the effective R value using exterior continuous insulation. So all these retrofits were done from the exterior of the building. There was no one living there at the time. It was summer, and like I said, these are student townhouses, but they wanted to do it without disrupting the interior as much as possible. Obviously, for the windows was a bit tricky. They had to go in to do the windows, but the rest of it was all done from the exterior. So very minimal impact on the inside. These are the R values they decided on based on the model. They wanted an R60 attic. Above grade wall was R28 effective. So a reminder, effective kind of takes into account the repeating thermal bridges like wood framing. Doesn't necessarily take into account everything that is now in the NECB 2020, but it takes into account the repeating ones. Foundation wall R20 full height. So the 5 companies that did above grade systems were BASF, who did a spray foam system, Drive It, who does EIFS, Insulspan did nail base, Owens Corning did XPS, and Rockwell did mineral wall or stone wall. The basements and attics, to keep things a little bit more easy to compare the performance of those manufacturers, the basements and attics were all constructed the same. In the attic, we had strategic air sealing. So they moved some of the fluffy insulation that was up there away from the top plates and away from the penetrations. They did strategic air sealing with closed cell spray foam over those areas. And then they put R60 insulation back on top. So the spray foam was less for its R value and more for its air sealing strategies and technologies. And we did closed cell spray foam again in the foundation. I'll show you a photo of that, and in the rim joist in the basement. And like I said, most enclosure work was done from the exterior. In terms of the windows, not going to get into a lot of details about the windows. They were new vinyl triple glazed. That's the U value range. We definitely increased air tightness. They did floor door testing before and after to confirm that they met the net zero energy requirements, as well as increased it significantly from before and after. And then they improved a lot of existing details and repaired as required. So, when I say improved existing details, that usually when you're opening up a building from the 1980s, that usually means you're adding subsill flashing around the windows, as well as potentially other air tightening measures. But subsill flashing is usually the most important and most typical one that people add. You can see here on the left, this was a window beneath a window that did have some water ingress over time. And so you can see some of the staining on the framing. It's there. It was still structurally good. It was pretty solid, but it had repeated long-term small amounts of wetting. The middle picture there is just insect damage in the XPS insulation. And some people might ask, well, is that a reason to avoid XPS or board foam insulation? And I would argue that it is definitely not a reason to avoid that. What happens is they won't go in there unless there's a source of water. There's a couple good, good experiences in the industry where, they had water over the surface of the foam, and so that gave the insects, a source of moisture. If the insulation is completely dry or there's no moisture, they won't do that. That is not a thing that they do. And then on the right side, you can see that there was obviously an issue with the flashing, the roof flashing at that transition between the roof and the wall, and it dumped water into the wall. And at the time of the repair, obviously the OSB was completely missing where it had rotted through. So this is, doing these deep energy retrofits gives us an opportunity to make repairs, make improvements to some of these areas. So just to lay out exactly what the retrofit looked like, there were 3 buildings. And so 2 of them had 4 units, and they were split into 2 because it was easy enough to do that. The cladding just went over the insulation. The insulation was matched, and it was transitioned, so you could do that. The Drive It one had 3 units, and it was on its own because it looks completely different. Obviously, eaves is going to look very different than siding, so there was no easy way to transition that. So they did an entire 3 section on eaves, and then the other 2 were sided with those different types of insulation. And so now we're going to get into the 5 different strategies and talk about how they were constructed. We're going to look at a couple architectural details of all 5, and then we'll get into the monitoring after that. So for the details, in no particular order, or maybe I put them in alphabetical order. I can't remember, but they're not in any specific order. BSF. So we had to remove the insulating sheathing, and they installed 5 inches of 2-pound closed cell foam against the drywall from the outside. So they sprayed into the cavity. It came out past the framing, so that and then they had the strapping. You can see. Let me see what I can do here. So you can see this horizontal strapping. They put this horizontally. They secured it to the exterior of the vertical wall framing, and then they filled almost essentially to the outside of that. So they covered the wall framing, so it wasn't thermal bridging all the way through. And then what they did was, on top of that, they put on top of that horizontal strapping, they put 2 inches of neopor, which is just a graphite EPS. And then they put a WRB because, so this one, there's a lot of pieces to this one. And so I will say also that these are all, there's lots of different ways to do this. And as you'll learn, there's 5 different ways just shown here that all work, pretty well. There's ways that are not included here that can also be done. So, and I don't want everybody to think that this is the only 5 ways to do it, or these are the best 5 ways to do it. These are just 5 ways that were just determined based on the manufacturers that were involved. So, it's not necessarily the way that other people would choose to do it, but the resources are there. So because EPS can't be used as a drainage plane unless it's faced and taped, they left it unfaced. So they had to put a membrane over top, and then they had the vertical strapping secured to the horizontal, and then they put the vinyl siding on that. So a few more pieces in that one. You can see here a detail. This is where they installed the neopor. You can see on the horizontal strapping. You can see here the spray foam goes all the way from the drywall out to this red line. And so that's where the red line indicates where the air barrier is, but the air barrier is all through the spray foam. It's not necessarily at that interface. And then they put on the 2 inches of neopor on top of that, the vertical strapping, and the vinyl siding. So that's the BSF wall. Drive It Outsolation MD. Most people are relatively familiar with EIFS. It's they put down a fluid applied WRB first. Every EIFS manufacturer has its own fluid applied WRB. And so they install that. And then they install the EPS foam. Usually, especially in Canada, it has to be drained. There was a lot of failures back, I think, in the 80s in the southeastern United States, where there was catastrophic failures with EIFS not draining. You could go in and poke holes in the EIFS, and it would just drain water out this hole. Like the water would just come out for a half an hour with all the water that got built up behind because it wasn't able to drain. And so they now have to be drained. Each finish goes on top of that, and then additional mesh reinforcement on the first story to increase the durability of each finish coat. One thing that a lot of people, I don't know if it's a pet peeve of mine, but a frustration I have is that everybody thinks that EIFS is not very durable. And it's true. It isn't always durable, but if you use the right mesh installed over top of the eaves, it can be incredibly durable. And they have, I love when the eaves manufacturers have demonstrations where they fire, at a trade show where they have a pitching machine and they fire hard balls at it, or they hit it with a hammer or whatever, trying to damage it, and you just can't if you design it right. So the problem is that oftentimes either they don't know, that the person designing it doesn't know, or it gets value engineered out because it is more expensive. And so therefore that really heavy duty mesh really just needs to go in places that are going to have the most risk of impact. So it is not it is a very durable, it can be a very durable solution. It isn't necessarily a fragile one. They did. Oh, the other unique thing about the eaves was that they put it right over the brick. They installed so they didn't have to take the time to remove the brick. They also didn't have the landfill, the brick in the landfill. And it does add some more, rigidity to the wall. You could say it adds some thermal mass. I mean, it's hard to prove how much that helps, but it can't hurt. And so the fluid applied membrane went directly over the brick finish in those cases. And they did have to, remember I said that there was no sheathing on this building, so they had to put a sheathing on the gypsum sheathing, and you can see the blue skin around the windows, but I flashed it to the gyp. And then you adhere the eaves and put the finish coat on. Owens Corning has the code board air barrier system, a code approved air barrier system that requires different gaskets, tapes, and combined with XPS insulation to make it very airtight. You can see, actually, you can see that they haven't got tape on the outside layer. They put tape in the middle layer to help protect it and hold it in place. And then the strapping goes on the outside layer. Yeah, right here. So the red line is where they actually consider the air barrier to be. So they tape all of the joints. You can see some of the Owens Corning tape on the joints in this area. And then they put on a second layer of XPS over top. So in this case, they left the bat insulation in and just used what was already there. Plastifab Insulspan. So this was another combination wall system. They installed a 1-inch Durafoam sheathing taped as the air barrier. So they have a faced EPS product here called Durafoam, taped it. That becomes the air barrier for the wall system. And then they installed the 3.5-inch EPS and OSB nail-based panels. So this was the only one that had OSB on the outside. A lot of trades, we find that when we're talking about adding exterior insulation, a lot of trades like nail-based because it most closely resembles traditional construction with the OSB on the outside, and they feel more comfortable with that. Typically, we still put strapping on this one because it's good to have a ventilated drained cavity behind your siding, and we want to keep it all the same. But nail-based products are pretty popular, especially with contractors just getting into the retrofit market and aren't as familiar or as confident with something like this where they put strapping on this. We are constantly, well, not constantly, but there's always a contractor that has ever done this before, and they're like, but how do you do that? How does it work? And so we have to explain it, the science and the loads. And so yeah, this was the nail base. You can see the side view here with the OSB on the other side laminated to the EPS, and there's some splines that go in. It's essentially a one-sided SIPS is another way of looking at it. And lastly, but not least, the rock wool solution. So for the rock wool, rock wool doesn't sell a membrane. So they used a Delta Vent SA vapor permeable self-adhered membrane. They had to install OSB sheathing. So I don't think any of the other ones installed an OSB sheathing. The Drive-It installed some gyp sheathing, but so they installed an OSB sheathing. They covered it in the Delta Vent SA air and water barrier, and then did these semi-rigid stone wool with strapping, which is pretty common, especially if you're working in the passive house market. They love this type of assembly with thick layers of rock wool and strapping. So it as we get more into carbon, we'll see what happens. I mean, one of the advantages of rock wool that we hear about all the time is that it doesn't burn, obviously, because rocks don't burn, but it does take a lot of energy to melt rock and glass to make insulation. So, that might might find that there's more or less intense insulation materials. So here you can see a couple details. They had to build out wood bucks around the windows in order to do this one. And the air barrier, like I said, was at the sheathing level, self-adhered vapor permeable membrane covered with 2 inches of insulation. The basements were simply spray foamed against the concrete and into the rim joist area. The wood framing was already there and it was already stood off the concrete wall, which you would want, and so they could get spray foam in behind it without moving it, which was great. So that worked really well. The attics, like I said, they installed some closed cell spray foam. Oh, maybe they installed it 2 thick. I couldn't remember this one, but they looks like they might have installed it 2 inches thick everywhere. But they definitely no. Okay, sorry. Because this was not a raised steel truss, at the edges of the attic, you get very little room for insulation. And so what they did was, in order to increase the R value per inch, they sprayed 24-inch width at the outside edge around the perimeter so that they could get more insulation in the available thickness, as well as seal any holes for wires, for switches and lights. And so that was what they did around the edge. They also sealed the tops of the interior partitions. Because it's a townhouse, the attic is actually partitioned between that townhouses as well. I mean, I'm sure everybody's seen that. You drive down the road on a cold day and there's a little bit of snow on the roof, and at every partition wall in the attic the snow is melted because heat has escaped up there. So we did our best to try and air seal those partition walls to avoid that chimney effect of the fire barrier between the attic hatches. And then they added loose fill insulation to reach R60. They kept what was there and just added some more. So like I said, they did do air tightness testing. They did do a demonstration of aero barrier. This because every time I presented this, someone's always asked. It was not required, but they did do it just to see how it worked and to watch the air tightness improve as they installed the sealant. But it was used in all the ductwork, which I'm a big fan of. I like including it in ductwork, especially in older ductwork, which was not sealed, as well at the joints. And so this is how this material and this technology was originally used. Was they would inject it into the ductwork, pressurize the ductwork, it would escape through the holes in the ducts and seal it as they did that. So the ductwork itself became much more airtight, and so you didn't lose as much conditioned air on the way to the registers. So that was done in every unit. So after all the enclosure energy saving measures, the windows, R value, they installed new HVAC equipment specifically for the lower loads they were going to expect. And so there were many manufacturers of heat pumps, furnaces, boilers, HRVs, air handlers were used for this project. They got a lot of equipment donated since they only needed 1 or 2 of each one for these 11 units. Every unit had a heat pump. Some of them were standard heat pumps. Most of them were cold climate heat pumps. And I'm really looking forward to a presentation, hopefully in the near future, on the energy use and mechanical performance. Of course, most people are aware that as you increase the air tightness of these older houses that don't have a solid ventilation strategy, you need to improve and add intentional fresh air, intentional ventilation. And so these were installed in in all 11 units, either a Van E or a Life Breath, to help with that. I mean, these are student residences, so it's hard to know exactly what the interior conditions are going to be in a student building, whether they, make noodles every day or they eat out all the time. It's impossible to know, or they take half-hour showers. So, these are incredibly important to control the interior relative humidity, especially in those types of units. I could take, if there are any, questions that are burning right now, I could take a couple before I get into the monitoring. But I will have lots of time for questions at the end too, so don't feel like you need to ask them. I'm going to stick around for a while afterwards. It's not a problem because I know it's running a little long. I'm battling a little bit. I get excited about this. It's hard not to. Okay. So monitoring. And this was one of the things I like the most. I've been doing monitoring of building enclosures for almost 20 years. This is how I started working for at the University of Waterloo. When I was doing my master's, I was working for John Straub and Chris Schumacher, traveling all over North America, in fact, building test huts for people. It seemed to be at a period of time where lots of manufacturers wanted test huts. It has dropped off significantly since then, but at the time we installed a bunch of them so that those manufacturers could determine, put in prototypes or determine the performance relative to their competitors, or just try to understand what's going on. So that's the data acquisition system that's in one of the basements. All the sensors have to run back to there. Here's two examples. We have a temperature and relative humidity inside this vapor permeable bag. And then you can see a wood wafer back here. So where oftentimes we will stick two stainless steel pins into a wood substrate, and we determine the moisture content by measuring the electrical resistance across those pins. As it gets wetter, electricity passes more freely, the resistance goes down, and we can correlate that to a moisture content. As it gets drier, the electrical resistance goes up, the electricity doesn't pass as easily, and so we know we can get a different moisture content. So, but where there's no wood, like where there's sheathing, gypsum sheathing, or where there's XPS insulation or concrete, we use wafers as surrogates. So we're measuring the moisture content of that wafer instead of the substrate. And so you can see we instrumented down here. You can see we did under some of the windows in every unit. We did on the concrete foundations to see what would happen there, because I don't think they were really well waterproofed on the outside considering how their age. So we thought we'd see that. The evaluation criteria for moisture content is we're looking for like 16 to 20%. Relative humidity is a little different because it does depend on the time of year, and it depends on the temperature, and it depends on a bunch of things. But really, if it's really high, that's risky for lots of things, and including condensation and moisture accumulation. So we like to keep it below 80 would be ideal. But again, that's not as set in stone as the wood moisture content. So you can see we always installed sensors at this level. So we always have them in the ventilation gap or drainage gap of the cladding. Now we would expect that sensor to be like really high humidity and really, follow the outdoor temperatures really closely. And so it's going to fluctuate all over the map. We don't usually learn a lot there. But here's where we kind of want to know the most, because this is where in cold climates, in typical wall construction, the problem is the sheathing. If we get leakage from the interior to the sheathing layer and it condenses, we get moisture accumulation and damage to the sheathing. So we always put them in approximately that layer, and that was the ones we were most interested in. Is there any risk of interstitial condensation? That's what we were looking at there. And then we always had a temperature here, but I don't even have any data from that one because that usually just measures the interior. It shows if there's any huge anomalies in in interior temperature, whether they run it like the tropics or whether they are maybe not home. It tells a little bit about that. So you can see the dark blue. So we're looking at the BASF wall assembly, spray foam, neopore. We're looking at these two sensors, right, or this RH right here, and you can see that it never gets above 80%. And we did this in two units, two side-by-side units. So you can see 52 and 53 were both done like this. And so we measured them both, and the measurement was consistent. The RH at this layer fluctuated between like 30% and 70%. And you might be, why did it fluctuate so much? And it's like, because the relative humidity is relative to the temperature. As the temperature changes, so does the relative humidity. So that's why it fluctuates a fair bit. We like to look at moisture content because it doesn't fluctuate nearly as much. And you can see here, over the 3 years, you can remember I said the evaluation criteria is about 16%. There's a couple issues with my graphing, but there should be a dashed line here to show that this never got anywhere near the critical moisture content at this layer measuring this moisture content sensor. So that's good. There's super dry. In fact, it's so dry that once you get below about 8%, our system can't measure moisture content. And so some of the, it gets spotty, the lines disappear. And so that's why in some of the graphs, you won't see many lines, is because it's so dry. So in the dry-vent wall, it's a little different because it didn't have siding, but we measured again right in this space, in the brick space, where if there was any issues, we would get moisture accumulation in this gap, because remember we left the brick on, so the gap is still there, and it does present a bit of a complexity in the system. And the brown line is kind of where we were looking at that in that space. It's the cavity. It's between the cavity bat and the exterior XPS for the condensation plane in here. And again, very, very low. And none of the relative humidities in this system, because none of them are in the drainage space, went much above 80%. So that was great. Again, moisture contents right at this layer, still, very, below 16, drying in the certain months so much that you can't read it. So that's a win. We're going to look at the Owens Corning one again. This is where we put it between the BAT, which is air and vapor permeable, and the XPS. And we fluctuated through the year, but it never went above 80%. So that's the RH in 2 units side by side, very consistent of the RH between the BAT and the XPS. Of course, the blue line is the one in the drainage cavity, which, like I said, will go to 100% almost every night as the temperature drops and the air cools. Moisture content for the Owens Corning wall, again, stays below 16%. I guess I should have given you a spoiler alert right at the start that this is data analysis is very boring. But in this case, that's exactly what you want. You want it to be boring. We assumed it was going to be boring, but we had to check. Is it more of a demonstration than it was research? Plastifab, so the nail base, we put it on the back of the, again, at that interface between the fiberglass bat and the EPS foam in two units. Very safe and very tight, very consistent between the 2 units. Moisture contents, again, at that interstitial layer, quite low, not even anywhere near 16%. Rock wool, again, at that interstitial layer between the wood sheathing and the bat, super low. And on this one, the 16% is up here, and I think this one wasn't the full data set, but it was repeated every year. I think this was only the first year, but again, it was absolutely no issues. So those are all the above grade walls for all 5 manufacturers. We look at the basement. We installed lower and upper. Basements are very complicated because they have an above grade portion which gets very cold and very hot, and they have a below grade portion which is very wet all the time because it's it's below grade, and its inward vapor drive is 10-11 months of the year, but the temperature stays very, very consistent because it's far below grade. It's like 10 degrees Celsius, so it can be difficult. So we put above and below grade to kind of see what the differences were. You can see the brown ones are the upper ones. They fluctuate a lot more in relative humidity because the temperature fluctuates, seasonally. And then the green is the lower moisture content or the lower RH. And so this is a bit of a weird thing. It took off here. And I think if we go to the next one, we see the moisture content also did that. And it's the only moisture content we measured that went above 16%. And so I just found this yesterday, so I didn't have a lot of time to look at it. But I mean, I would definitely want to keep my eye on this. I mean, it isn't that high, and it is trapped between the concrete and the spray foam, neither of which is a moisture sensitive material. So we'll see what happens over the next year and a bit and see if there's something we need to look into there. But that was the only anomaly in the first 2 years of monitoring at any of these locations of something that looked a little bit weird. And so the winner, everybody asked, well, which is the best one? Well, what would you say is the best one? So I'm going to tell you the best one. The winner's the Planet. It won because they all performed very well. They all exceeded expectations, or at least met expectations. So the Planet and the reduced greenhouse gas emissions and reduced CO2 by this energy and the increased durability. So mechanical monitoring. So these are the types of things they did monitor in order to compare. And so we looked at whole house electricity consumption. There was a weather station that was installed. There was interior space temperature and relative humidity, HRV temperatures, airflow, electrical consumption, all the typical things you would expect to see, and which I hope will be going into the comparison. The next question I'm going to cut off before everybody asks is like, what were the costs for the project? How did the costs compare? Because that's important. Don't get me wrong. The problem is with this job, it's almost impossible to determine what the cost was for the project and the cost were for the individual materials, because there was so much stuff that was donated, and there was, students that were helping do some of the analysis. There were services that were donated, mechanical equipment, installation, and it was in that aspect, the costs were lower. But then in the whole total increased complexity related to multiple designs and the architect having to deal with all these different things, the costs were higher because it was the same project and they had to deal with all that and then the integration. So it's impossible to know the costs, unfortunately. And so we're getting to the end here of the summary. They did successfully accomplish net zero ready certification, so that was exciting. And they did it with everything we talked about. They increased the levels of insulation and airtightness. They have high efficiency heating and cooling equipment, support from Enercan LEAP and the OERD's building infrastructure program. They had donations of equipment, installation, time, and funding. And they had buy-in early from all stakeholders, including the college, general contractor, consultants, product manufacturers. They got everybody on board and then started the project. They didn't start the project and then try to get everybody's kind of direction changed, which happens almost too often, that they try to figure this out after they're already in the process. And then, yeah, we have enclosure and mechanical monitoring. And so we looked at some of the enclosure monitoring, obviously nothing too exciting there. And so hopefully we can get some presentations on the mechanical monitoring to kind of compare that. A couple challenges that I want to note. This was actually done during COVID. So there was challenges related to that. So it was delayed a year to begin with. And then, it was just site access and things were a little bit tricky at the end of COVID, as everybody remembers. Some scope clarity issues. So there were so many people involved, including manufacturers, contractors, the architect, and sometimes it was hard to determine whose job was what in certain areas. It's like, well, was the contractor bringing that installation and installing it? Was the manufacturer providing someone to install, like in the case of the spray foam, those types of things. And it wasn't always clear. And so there was some confusion and some delays because of that. There was a shortage of skilled labor during the project. The skilled labor that was there was not used to the high performance construction and the level that was required of this project. So that was a bit problematic at times. Work required checking in terms, for airtightness and other things. And then the HVAC contractors' quality of work. These were high performance buildings. I don't think they were used to that. There were some issues there in terms of like some of the settings, some of the just troubleshooting. And one thing I thought of as I talked to, John Coco was kind of he's a well-known, HVAC expert in Ontario, and he was kind of in front of the project manager as well as dealing with the mechanical stuff. And so my question for him was, who normally checks all this stuff in a construction project? Who normally would identify that the dampers require replacing on an HRV that was installed and left there? It's like, well, I know the answer is nobody, but it's like so that worries me a little bit in terms of high performance buildings. This picture is not from the project, but it is a funny story where RDH did some mechanical design for a project in Toronto. And 3 years later, we get a call. They're like, you're supposed to do general review of this project in order to get the building permit. And we're like, yeah, okay, that makes sense. We did say we'd do that. So we went to site, and this was where an HRV was supposed to be. They ran all the ducts to it, but nobody ever put the HRV in. So it was, and they'd been living there for a year, and you just, how do you know? As a homeowner, you don't. And so that's a challenge that I think is difficult to overcome. Lots of people involved, from a construction, building, consulting perspective, and then even more from a manufacturer of mechanical equipment and resources, product manufacturers, things like that. So that I went a little long. I apologize, but
all good.
I will now take any questions.
Yeah.
Oh, wow.
That was an excellent presentation, Jonathan. That was a pretty cool project to see, almost like kind of like real-time mock-ups on each one of those buildings to get a sense of how they actually perform in the wild, which is really cool. I can see there are quite a few questions in the chat, and I know I've got a few myself, and so maybe I'll kick it off with one here, and then we can open it up to anybody else who wants to jump in and with their question. I have a little bit of familiarity with this project. I've done a little bit of research on here, and something that was you mentioned that data logging and that information is kind of boring, but this is probably the perfect crowd for boring. I think all of us here like that kind of thing. And one thing I didn't hear you speak about was blower door testing. But I do know that when you did the blower door testing on these buildings, or when it was done, there was kind of a method that maybe not all of us are familiar with when testing multi-unit um, buildings like this, and maybe a guarded and unguarded blower door technique. Do I have that right?
Yeah. Can you still see my screen? Is it still showing or no?
No, it's not.
I'm going to put it back up because I think I have a slide. I just took it out of the presentation because I knew I was going to run long.
Yeah.
Let me see what I got here. So yeah, there was unguarded and guarded. And so what that means is, for anybody who's unaware, is if you run a guarded blower door test, or no, let's start with unguarded. So you go up to a multi-unit townhouse and you run a blower door test on one building or one unit. And so what you're doing is you're essentially measuring their leakage, both of the enclosure and between the units. And so in order to run a guarded test, in order to just get the enclosure of that unit, you have to pressurize every adjacent unit, and in this case, there'd only be two, to the same pressure. And so that way, you don't get any leakage across the units because they are pressure. Because air leakage is only driven by a pressure difference. So if you have no pressure difference, you can't have air leakage, and so you get it just on the enclosure. And there were criteria for both unguarded and guarded, I think was your point, is that you could do either, and that the criteria were different. I think the guarded result required 1.5 ACH at 50, and the unguarded required 2 ACH at 50 pascals. And that would have just assumed there was another 0.5 coming from the units in order to get the certification. So, yeah.
Interesting.
Then I guess, I don't know, did that answer your question? Was there?
Yeah. I
more
think
of a
that's just probably a
statement?
little different
Okay.
from what most of us are used to in like single family residential projects where you're just running a standard test. I remember hearing you speak about this before and thinking that was quite interesting. Anyways, I'll pass it over to Justin or Lori if you have any questions you want to add to that before we open it up to the gang here.
Well, the thing I've been wondering about, because I'm on the design side. I don't think I told you. I was too busy talking you all about how sleep deprived I was when we we started the show. I didn't even
But
say
you're
what I
still
do,
here,
but
so
I'm an
you made it to
architect.
the end. Great.
I'm a building science specialist, but I own an architecture firm. So I'm always like interested in the design. And so Peter had a similar question somewhere in the chat, and I don't see it right now, but really interested in how the decision making process went around had to pick your assemblies. What was the
Mhm.
thought process around that?
So I don't know how they picked the manufacturers, but they basically picked 5 different types of manufacturers to be involved. And the manufacturers played a big role in determining they were basically bringing what they thought was their best set of details for this type of construction that they would hope to take from this project and go out and do more of it. So the manufacturers are the ones that set the details. And they were providing insulation, like they were basically donating insulation. So,
Okay.
and we just kind of reviewed it. We talked about it. There was some fine tuning that was done as part of the process, but basically it was the manufacturers themselves that determined what the wall construction was going to be essentially.
Yeah, great. Like, really curious to know. Yeah, I'm like, why? Anyway, we'll never know since it was the manufacturers. Um, Justin, do you have any questions?
Yeah, I was kind of listening along. I'm a big believer in the IDP process, and we run that on our new construction as well as some of our renovations. And yeah, I was just curious how you guys came about those assemblies. And then also a big one for us in our region, we end up with a lot of structural right into the foundations that when we're talking about costs and the money that we're going to be putting into some of these deep energy retrofits. that, in that early processing, we're actually analyzing the structure, the foundation, everything to make sure that, that it's worth putting all of that money into it, right? So, I mean, I could see there that I don't know that that was much of a concern short of maybe some of that exterior sheeting that was not, in the original construction, but
Yeah.
yeah, no, very interesting.
No, yeah, that's a good point. Is that, yeah, you'd want to check that for sure, depending on the age of the building and the type of construction. If it was like a rubble foundation or you had below grade masonry or something, you'd obviously want to look at that, the condition of that. But yeah, they weren't concerned about that in this project. The one thing they did replace a bunch of porches, so that had really nothing to do with the enclosure, but that was kind of the only part of the building that had deteriorated to a point that they had to repair it, the concrete and stuff, during the project. So. But
Right.
yeah, obviously we got to look at that and make sure it's appropriate to retrofit.
All right. I think Pete V had a question early on. Do you want to jump on here, Pete, and ask your question?
Looks like Pete has multiple
Yeah, I
questions.
think there's
So
a few there.
Lori, you got my question, so thank you for jumping in about that, about the assemblies. I'm real dark right now because the power's out currently in our spot. But I think the question that didn't get asked quite yet is data loggers. What's your preferred product? What's worked successfully for you?
Yeah.
What's a decent product? And open source would be even better.
So what we've used so when I started, like I said, I started doing test huts, test buildings, data logging, data acquisition about 20 years ago. And John Straub and Chris Schumacher had already kind of developed a system at that time, and they used Campbell Scientific as their data logger of choice. And the reason they did that, it is slightly more expensive than some of the other options, but the programming language it improved a lot since then to now. It's more of a basic and not a machine language. But the reason they did that was because it was the only one they could measure the moisture contents on. And I'm not a circuits guy, but it had to do with the internal impedance, I think, in the logger. You needed a certain amount in order to measure the resistance across the wood. And so you couldn't do it easily with like National Instruments or some of the other ones. You just couldn't do it. So that's what they developed the system with, and that's all we've ever used for the big systems. Unfortunately, it's all wired. So that is one downside if we're looking at pros and cons of the data acquisition system, but it's incredibly accurate. It's easy to use if you have experience. They provide a lot of support, and they build weather stations that already link to it. So that's what we've used over the years. If we're doing something smaller, we would use maybe an onset Hobo Bluetooth system. I know the West Coast, they like to use shoot. They started off in roof monitoring. Oh, I feel bad for not remembering their name. SMT, thank you, Ben. SMT. And so you'll find that SMT sensors looked exactly like our sensors about 15 years after we made them. But copying is the best form of flattery, I suppose. So they do wireless systems and they do wired systems mostly on the West Coast. Where they initiated, and they mostly into roof monitoring systems, but they do some data acquisition as well. So, but yeah, Campbell Scientific is what we would use.
Cool. See, Al has a question on here regarding HRVs. Al, do you want to jump on and ask your question?
Sure. Yeah, just when it came to putting the HRV, doing the installs and getting the ductwork out from the units. I presume each unit had their own HRV. So yeah, did you guys have some issues there around, okay, so where do I get the ductwork out? Do I have separation or not? What kind of workarounds did you have to do there? You had to do any?
I don't remember any challenges with the ductwork. I mean, all of the units had air handlers already. So it wasn't like we had to come up with the ductwork to distribute it. But I don't remember any issues or challenges with placing the ductwork. I think just the way it had been previously set up, I think it allowed it to work pretty well.
Okay, so
I don't,
yeah,
I don't,
on the outside walls basically to get the
yeah,
ductwork out to the wall. Okay,
yeah.
good, thanks.
Thanks, Al. I see Peter Molyneux was active in the chat. Did you have a question in there, Pete, that you wanted to ask?
No, particularly just observing the great project that it is. A nice opportunity for comparison of procedures and projects, how they can work together and how they work differently from each other as a system, each one. No, great commentary, great description. Thank you.
Yeah.
Excellent. Anybody else out there have a question they want to fire off here before we wrap up? It looks like that might be it for today.
I have one last question, but I
Yeah.
do want to go to bed, so I'll shut up afterwards. I'm just curious if there were did anything surprise you guys, like as you did it? Was everything kind of the results as expected once you got into the monitoring?
Once we got into the monitoring, I think the results were pretty much what we expected. We've done some monitoring of these types of enclosures before with like exterior insulation, and we usually will get very low moisture contents. We don't get excessively high relative humidities once you have the exterior insulation. We've done a lot of research on exterior insulated wall assemblies. There was a bunch of work done at the University of Waterloo Beg Hut by like Trevor Traynor and Mike Fox. We had a test hut actually on a building in Burnaby, BC for 10 or so years with Govan Construction. And we looked at there's 7 walls on each side. We did exterior insulation all over the place and looked at the difference to those. And test huts are more interesting in a way because you can really crank up the relative humidity and you can intentionally stress the walls by injecting water. So it's never boring because you're usually stressing them on purpose that you can't do in a normal building. And so you get to see how they dry and how the moisture moves. And so, I mean, because of all just the knowledge that is in the industry and that we have from our wall testing all over North America, it's like we're pretty sure that unless there was a construction defect, we weren't going to see any moisture, because of just the R value ratios and the exterior insulation, which, I mean, I think should be becoming more and more common knowledge that is the most energy efficient, durable way to insulate a building. And lots of builders are still catching on. Lots of builders are just doing the code minimum, and that doesn't always require exterior insulation. But that's the way we're going to have to go eventually to get energy efficient, durable buildings. And I mean, and you could use lots of different. I think the one thing to take away is that you can use lots of different strategies, lots of different insulations. It doesn't have to be vapor permeable. It doesn't have to be vapor impermeable. You got to use exterior insulation and design appropriately depending on what you pick.
Yeah. I was going to say you could take the word eventually out of that sentence. I think that's the way we need to do it now.
It would be nice. It's a hard sell still. I mean, I've been working on exterior insulation for over 10 years and talking about it and testing it. And it's like, yeah, it's still a bit of a hard sell.
Just I got one last quick question.
Yeah.
Sure.
About the vinyl siding.
Mhm.
So one of them got vinyl siding. So how do you recall how the installers felt about doing that vinyl siding work with those types of building assemblies? Were they perplexed?
I think the people that installed the vinyl siding had no issues at all because they were installed. I mean, I don't remember the breakdown of who did what work. So,
yeah.
But I know the vinyl siding on every house went on vertical 1x3 strapping, and so that should be relatively straightforward to most people. I mean, there's only one place to put the nail, and so I mean, I think it worked well. I don't remember hearing any issues with that. And
yeah, just my own experience here. We were looking at doing vinyl siding on this retrofit, and I'd have strapping every 16 inches.
Yeah.
if you don't have a vinyl siding without something bonded to the back, like styrofoam or something, the manufacturer would just basically say, well, there's no warranty, because if it oil cans on you or something with their, wind pressure and stuff, they're gonna go, well, sorry, it's against the rain screen and it might buckle, so too bad.
Yeah, and I mean, yeah, and I just like to, as my boss would say, is like, where are the dead bodies that show that it doesn't work? It's like, we've been putting it on strapping for years already, and it's like, I have not heard of any failure, or at least not widespread. Maybe I mean, if there's failures, it's probably more due to the installation method than the fact that it's on strapping. I would have to
Yeah.
guess. So my sense is that they just need to catch up a little bit in terms of that, or maybe you just, I don't know, maybe you just don't care about the warranty. I don't know. I don't know what the correct answer is, but I've never heard of the fact that when you put it on strapping causing problems, unless there's an installation issue with that vinyl siding.
Yeah, I haven't either, and I was a little bit shocked when I got that answer or comment.
Well, warranties are like, you're relatively useless anyway most of the time, because they're always going to find something to get out of paying in a lot of cases. I mean, I don't know. That's maybe a bit of a generalization and a cynical attitude, but it's true. They try to do everything they can to get out of paying. So anytime you do something a little bit different, it reminds me of unvetted attics and shingle warranties. It's like, until a shingle company owned a spray foam company, they didn't allow that to happen.
Yeah.
And they did.
Yeah.
Awesome. Well, in an effort to keep Lori's bedtime intact, we'll bring this to a wrap and say thank you to Jonathan for a really good presentation. And I'll maybe give everyone a heads up on next month's presentation, which will be October 16th. And BS&BEER's very own Sean St. Amor will be doing a presentation on his current project, which is on Beatty Street. And it is a century-old warehouse in downtown Vancouver, built in 1911 and originally constructed with heavy timber post and beam. And this project is a redevelopment that includes new office floors, amenity rooftop space, activated street front retail, laneway retail, cafe uses, and all built to LEED Gold standard and expected to complete around 2025. Sean's going to take us through a history of and revitalization of this amazing building. So definitely tune in to next month. And Sean's definitely familiar to, I think, all of you on here. And I'm sure he'll put together an excellent presentation for everyone. So yeah, thanks, guys.
Thanks, everyone.
Yeah, have a great night, everyone.
Good night.
Yeah, thanks a lot, folks. Appreciate it.